Hello, my listener and also the viewer of my slide. I'm going to explain current electricity. In the previous lessons, we talked about various terms such as electromotive force, potential difference, current, resistance. We also looked at arrangement of resistors, both series and parallel arrangement. Now, in this lesson, we are going to look at numerical examples on this topic of current electricity, how to solve numerical questions. So this is very important, and at the end of the lesson you should be able to work out potential difference or current in any circuit that you can be given. Now, in our first example, the question goes as follows. Two cells, each having an EMF of 2V and an internal resistance of 1 ohm, are connected, A in series and B in parallel. Find the current in each case when the cells are connected to a 2 ohm resistor and the PD across the resistor. So in order to work out that, we look at the series arrangement first. If the cells are connected in series, the total EMF is the sum of the individual EMFs. So 2 plus 2 will give us 4 volts. The total internal resistance is the sum of the individual internal resistances. 1 plus 1 is equal to 2 ohms. The external resistor is a 2 ohm resistor, and using this formula, E is equal to current into external resistance plus internal resistance, we can be able to get the current flowing, and that current will be 1 ampere. Okay, so now in order to get the potential difference across the 2 ohm resistor, that will be the current times the resistance, that is 1 times 2, that gives us 2 volts. So this means that if you connect a voltmeter across this 2 ohm resistor, it will read 2 volts. And if you connect a current in series with the external resistance, then the ammeter will read 1 ampere. Now, when the cells are connected in parallel, the total EMF is equal to the EMF of one of them, since those cells have got equal EMF. They are identical cells. The internal resistance is the product divided by sum, since we are talking about two cells. So it is going to be 1 times 1 over 1 plus 1, which gives 0.5 ohms. Now, using the same formula for electromotive force, we are able to calculate the current. So substituting into that formula, current is the only unknown quantity, and that gives us the current of 0.8 amps. And so we can also get the potential difference across the 2 ohm resistor as being 0.8 times 2, which is 1. From this diagram, the internal resistance is 0.5. So it means that the current is going to be 10 divided by 5, which gives us 2 amps. So that's the current produced by the cell. The PD across the 3 ohm resistor is equal to the 2 times 3, which gives us 6 amps. And that is the same current that comes, the current is 2 amps, because that's the current which comes from the cell. And by the time it gets to the 3 ohm resistor, it has not yet split. There is no junction yet. The junction is immediately after the 3 ohm resistor. The PD across the 2 ohm and the 6 ohm resistor is the same, because those two resistors are arranged in parallel. And so the PD is also equal to the current of 2 multiplied by the effective resistance of those two resistors. And therefore effective resistance is 1.5 volts, 1.5 ohms. So 1.5 times 2 gives us 3V. So the PD across them is 3V. Now, using that value, we can get the individual current across each of those resistors. That means that we'll have 3 divided by 6 giving us 0.5 amps, and 3 divided by 2 giving us 1.5 amps. So the current of 1.5 amps goes to the 2 ohm resistor, and 0.5 amps goes to the 6 ohm resistor. You can see the total current still remains 2 amperes. All right, now let's look at the third example. In this circuit, we have a switch. In the circuit shown, the battery has an EMF of 20 V, negligible internal resistance. Find the reading of the ammeter when the switch is open and when the switch is closed. So once this switch is open, the implication of that is that current does not go through it. Current cannot pass through this section when the switch is open. So the 2 ohm resistor, which is on the upper side, becomes redundant. So we only have one resistor which is in the circuit. Current will only flow in a circuit which is complete. So therefore the 3 ohm resistor and the lower 2 ohm resistor are in series. So we find the effective resistance by adding 3 and 2. And when that switch is closed, it means that the 2 ohm resistor is now also included in the circuit, and therefore those two resistors are in parallel. So going by what I have already explained, we can therefore calculate the current in the first case with the switch open as being 4 amperes. And when the switch is closed, we will have to first get the effective resistance of those 2 ohm resistors. The 2 times 2 giving us 4 over 4, which is 1 ohm, and 1 ohm added to 3 ohms giving us 4 ohms. And substituting in the formula for electromotive force, we get a current of 5 amperes. So that is how we handle the case of calculations under this topic of current electricity. The voltmeter is just an instrument that is used to measure potential difference, and it is always connected in parallel with the component, in this case a resistor. So whenever a voltmeter is connected in parallel with a resistor, it reads the voltage, and that voltage is the value of V, the value of IR that we have seen in these examples. So voltmeter is designed with high resistance so that it does not draw any current from the circuit to which it is connected. So that is how we handle numerical questions on this topic. I would like to thank you for listening to me. You can now go ahead and do a number of calculations related to this. Thank you.